bigger than 0, then there's some point past which all the elements are bigger than L over 2. Okay? And John says, well, given a sequence, we say, so you don't need to say this part because it's already given to you, right? So we say xn equals L, if blah, blah, blah. So maybe we can clearly say this means, that given any blah, 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 blah. Okay. Okay, rather than say, we say this happens if this happens. But anyway, it doesn't matter that much. This means that since we suppose that, since the limit of xn is L, for epsilon, so take, this is just more usual, take epsilon to be L over 2. Okay, then there exists an n such that this is the distance from xn to L is smaller than L over 2 for all n bigger than n. Now, this condition, xn, the distance of ln of xn to L is less than n over 2, is equivalent to this, right? By some earlier problem, which if you add L to it throughout, you get this, right? And so, right, and you notice that this thing implies that xn is bigger than L over 2, right? Thus, if the limit is L, blah blah blah, right? So, right. So you could say, I mean, you don't have to reiterate this, just in terms of writing, you could say, so we're done, right?
Because it's self-evident by the end result.
Well, I mean, you already said there exists an n such that this happens. Now this implies, xn is bigger than that xn is bigger than L over 2 as designed, right? I mean, maybe it's not wrong, and maybe it's yeah, it's okay to say this. This is fine, right? But it's sort of it's sort of redundant. And to make it completely clear, you'd have to say that n over there. There exists an n, namely that n, right? And then it becomes even more redundant. Okay, so yeah, so if I were me, just in terms of writing, I would say, and this is sort of redundant. No, you'd say, what you do is you come here and you'd say, in particular, xn is bigger than L over 2. Okay, and that would be it. Yeah, so that's perfect, basically. Right? I mean, writing-wise, there's some things that I may change, but the argument is fine, and the writing is basically fine. So why did you want me to? Did you have any question about this? Or
yes.
What was the question? Yeah.
Oh, as you just mentioned, the grammar of it.
Oh, okay. Okay. No, I'd say.
So, for example, in the first part of the proof, I basically bring back the definition of a bit of a sequence.
Yeah.
And then I wasn't sure how to mention it properly. And then,
I mean, you could say, by definition, right? By definition, this means that. So in some sense, you don't even need to say all of this thing here. Right? By definition, blah. Take epsilon to be L over 2, right? So you could have cut out some language.
Another thing. Is it okay if I just take an arbitrary epsilon value? Because in the definition it says given any epsilon.
Right. Yeah. Given any epsilon, this you can find an n such that blah, right? So take epsilon. Let's choose an epsilon. Take epsilon to be L over 2, right? Then by definition there exists an n such that this happens.
Another thing is on my homework I showed that L over 2 is greater than 0 since L is defined as greater than 0. Like I don't think you meant wrote it on the board, but I did mention it in the homework. Do I need to say that?
No, I mean maybe technically yes, but I wouldn't.
It is also evident.
That's pretty evident.
Okay.
Yeah. I mean, yes, such a thing. L is bigger than 0. You know that if you multiply any inequality by a positive number, right, then the inequality stays still. Right. So I mean, yes, if you want to be sort of nitpicky about it, then you have to cite one of the field properties. Right.
So yeah, that's one thing I'm wondering. To
Yeah.
what degree should I be picky?
Yeah. So I'd say at this point start loosening up a little bit. Right. So up until this point, we wanted you to say like everything that you do, make sure that you justify it. The reason for that is to make sure that you know when you're making an assumption or not, because sometimes you actually are making an assumption and it's not actually clear that you're making an assumption. So for example, Katie. So how do you know? I think it's best to err on the side of being more rigorous than less rigorous, right? At the beginning of the course, I told the graders, be very nitpicky about things. Okay. Now I think I'll tell them, loosen up a little bit. Okay. But I think it's necessary for you at the beginning because, for example, Katie came with. You remember you had some problem to show that x squared. What was it? X squared minus a squared. What was it? What was this problem from the group homework? I don't remember.
If x squared is less than b squared, then negative a is less than x.
Negative a is less than x is less than a? Right. Okay. Yeah. Yeah, this was the problem. Okay, so Katie came up after class and said, I have this other way of doing it. And said, well, look like this. Try this. X squared is less than a squared. That is the same thing as saying this. Okay? I think nobody will agree with that. Nobody will disagree with that. Right? Now you factor the left-hand side. Okay. Factor the left-hand side. Nobody's going to disagree with that. That's algebra. Right? And then she says, this is less than 0. We know a product being less than 0, being negative, implies that that one factor is negative and one positive. Okay, one factor is negative and one positive. Okay, right? So, do we know that? Do we know that? We do know that, but actually, that to be proper, you should justify that using field properties. Okay, we can do it using the field properties. Okay, but okay, some of you are like rubbing your heads, like, oh my god. Okay, but it's true, right? This is not. It's look. We had to prove that 1 was bigger than 0, right? Right. So if we're doing that sort of thing, then we can't just jump to this sort of thing. Okay. So this it's true, and you can do it. Maybe I'll give it as an exercise. No, you're not going to. Right. But you can do this. You can do this using the field properties. Okay. So true by the field properties. Properly. If this were said in the homework, the graders would be right to say you need to justify this using field properties. Okay. Because there's an assumption here. Right? There's an assumption that this actually is a claim that needs justification, right? Okay, so but suppose you justify that using the field properties, then that would say then either you have two cases. Either one, x minus a is less than 0 and x plus a is bigger than 0, or x minus a is bigger than 0 and x plus a is less than 0. Right? So there's two possibilities. Either this factor is positive and this factor is negative, or this factor is negative and this factor is positive, right? And in that case, x is less than a. In the first case, you get x is between negative a and a. And the second case, you get x is bigger than a and x is less than negative a, right? Which leads to a contradiction, which is impossible. And so you see that this follows. So that's actually a nice. That's actually the way we did it was by contradiction. And so this is impossible. we did was by contradiction, but this is actually a nice direct way of doing it. Yeah, so that was good. But again, you have to watch out for where you're making assumptions. Okay. Yeah. Okay. Any questions or reactions? I know, it's irritating, but you have to, that's, once I have to make sure at this point that you actually are capable of seeing what assumptions you're making and justifying them. Okay, because this is to prepare you for later courses. You have to be very conscious of what you're doing when you're doing mathematics. Okay. So so the stuff we're doing right now, as I said, is really the beginning of analytical arguments. So this is analysis. This epsilon stuff. Generally, one breaks analysis into two parts. One part is called hard analysis. The other part is called soft analysis. It doesn't mean that one part is harder or the other part is easier. It's just a description. And this is what one calls the hard analysis. It's all sort of like epsilon, like tinkering with epsilons and stuff. This is the beginning of that. Okay, so let me. Okay, so let's recall again epsilon-N style arguments. Okay, so again I'm going to start with the dumb example, right? Right. So remember that the limit of xn is L as n approaches infinity means, given any epsilon, there exists a time such that if n is past that time, then the elements are all within epsilon of L. So recall the definition. Okay, definition, you know it. The dumb example. An equals L, let's say An equals C for all n, right? Say this, you have a constant sequence, right? And somebody says, prove that the limit of A sub n actually is C. Okay. So what's, yeah.
Can you just clarify what the level n is really big and means in the term of the
So here's the picture. So the picture is this. We are saying that the limit is L. Okay. So it means that given any length epsilon, okay, given any distance epsilon, you can find a time. You can find a point past which everybody is within epsilon of L. Okay, you can find a point past, and this point depends on your epsilon. Okay, it's a function of epsilon. If I change my epsilon, that point's going to change. Okay, that point is allowed to change. Okay, so here's the dumb example, right? Suppose your sequence is constant, right? Well, want to show, so I'm going to be very pedantic about this. You want to show that given any epsilon, there exists a time such that if n is bigger than n, the distance of A sub n to C is less than epsilon. Okay, that's what you want to show. You say, well, given epsilon, take n to be, take any n. Just take any n. Right? Because because if n is bigger than n, we know that a sub n minus c is just c minus c, right? Which is 0, right? And 0 is certainly less than epsilon. Right? Because we're looking at a constant sequence, right? So you take any n and you say, well, no matter what n you choose, past that point, the distance of a n to c is less than epsilon, right? Epsilon was some was some positive number, right? Certainly, past, if I take any n, it's just I can satisfy your tolerance. Okay, so make sure that that's completely clear how to make this sort of argument, right? Because if you can't make this argument, you can't make any other argument. Right? This is the most basic of arguments. Okay. Any questions? Any questions? Any confusion? Yeah, Mia.
When you're making this argument,
Yeah.
are you often trying to just show that the distance between the function and the limit is less than epsilon?
Yeah. So the game is to find the point past which the distance between the function and the limit is smaller than epsilon.
Okay.
So you say, so you generally involves some scratch work. You look at, generally you do some scratch work and you say, let's look at a sub n and look at the limit and see if we can make that thing less than epsilon if n is big enough, right? And then figure out how big n has to be for this to happen.
And then if you just find any n, you can say that it's true.
Yeah, if you find the right n, then you can. Once you find the n dependent on epsilon, then you give the argument. Then you give the formal proof as they do in the text. Okay. But in this case, the distance between the function and the limit is 0 always, so you don't have anything to worry about. You can pick any n, doesn't matter. Right. Okay, so let me have you do a quick exercise. Take 3 minutes and prove the following. Give the argument, show that the limit of 1 over n squared plus 1 as n goes to infinity is actually 1. If you know what you're doing, this should take about 2 minutes. So you get 2 minutes. Okay, turn to somebody nearby and talk with them, please.
I got to this point, right?
I said let equal for like epsilon equal 1 over n.
This
And
showing
then
this
n is
curve
bigger than n,
is
and
the
1 over
same
n squared is
as
going to be smaller than
limit
1
to
over
this
n.
thing is
So
zero.
then it's equal to 1. Yeah.
Because something plus 1 is 1.
So this, I just did this. So
Becomes
let equal
limit
1 over, or epsilon equal 1 over n, and then you get this with plus 1 minus the limit is less than epsilon equal to 1
Well,
over
that's
n. Yeah, yeah, and then you just get this, so 1 over n squared is less than 1.
Okay, would somebody like to say how they did it? Would somebody like to say how they did it? So you want to show, right, that given an epsilon, there exists an n such that if n exceeds n, the distance between, what should I write here? What did I write here in the bars? Pen?
n minus 1, which is 1 over n squared plus 1 minus 1.
Okay. So we're looking for an n. So here's the sketch work. We want such that n is bigger than n, then such that this implies that this is smaller than epsilon. Right? Okay. So you say, well, okay, that's the same condition as this. Right? That's the same condition as this. That's the same condition as this. Right? Right. So, what should I do? What do I do from this point? What do I do from this point? I shouldn't look at people. What should I do from this point? What n do I need? What n do I need so that n bigger than n implies this condition? Right? As long as what n do I choose? What n do you choose, Mia?
Any n bigger than 1.
Any n bigger than 1. Any n bigger than 1. So if I say, so how does n, so let's take n equals 2, say. Okay? If little n is bigger than 2, how does that ensure that n squared is bigger than 1 over epsilon? For all epsilon. The answer is it doesn't, right? It doesn't. Okay, so the n you're going to choose, will be dependent on the epsilon. Okay, will be dependent on the epsilon. So you say, well, let's do a little bit more work here. Oh yeah, how?
That was my question. When you're picking your n's, aren't you kind of technically picking your epsilon first?
Yes, yes. Your epsilon is fixed. Your epsilon is epsilon.
Your epsilon is epsilon?
Yeah,
Don't
epsilon.
you pick an epsilon?
Yes, it's epsilon. It's a
Okay.
fixed epsilon.
Oh, I see.
It's a fixed number called epsilon. Yeah, and the n will depend on that epsilon. Okay, it's not that you have to do this for all epsilon simultaneously. There's a number epsilon, right? So given an epsilon, there's an n depending on that epsilon. There's an n depending on that epsilon, such that this happens. Okay, let me just go through. So we want an n so that n exceeding n implies this, right? Everybody okay with that? Okay. This is equivalent to this. Everyone okay with that? Right? Because we know that our n's are natural numbers, so I can get rid of the opposite values. Right? N is a natural number. Right? And this is equivalent to this, right? I just multiply both sides by n squared and divide both sides by epsilon, right? So, yes, medium.
Can you just let epsilon equal big N?
Let n be big epsilon? Okay, but then you have to tell me, how does,
Well, because then you get 1 over big N is less than n squared.
so then if n is bigger than epsilon, so let's try it. Let's suppose that n is bigger than epsilon. Does that ensure that n squared is bigger than 1 over epsilon? Show me that that's true. If n is bigger than epsilon, does that ensure that n squared is bigger than 1 over epsilon?
If it's in the natural numbers, isn't that true?
Let's see if we can show that, right? Right. If let's say that n is bigger than epsilon, does that actually give it to me that n squared is bigger than 1 over epsilon? Everybody think about that for 1 minute and see if you can come up with a proof or an example where that fits. Ichen, go ahead.
We could find an counterexample. So
Counterexample.
let's say epsilon is sigma 1. We can choose n number n equals maybe 2. And n squared is 4, but what over epsilon is 2?
Okay. So no, it doesn't work. Okay. Good. Okay. Let me. But yeah. So it's good. Make guesses. It's good. Make guesses, but then see if they work, right? This one here, you can do in the following way. Okay. You say, well, this is actually the same thing as saying that 1 over root epsilon is less than n. Okay. And this is, again, this would have to be proven, but it's in fact true that if a and b are bigger than 0, then a bigger than b is equivalent to a squared bigger than b squared. Okay. And again, if you want to prove that using field axioms, you can. Okay, it's true. But, okay, I'm just going to assume it. Or give it as an exercise. Okay. So now it becomes clear what we need to do, right? We're going to take our n, just take capital N to be something bigger than this, right? So if n is bigger than 1 over root epsilon, we see that n being bigger than n would imply this, which is the condition that we're looking for. Okay, so let me write it up. So that is the scratch work, and now we put down the proof. The authors call it the formal proof. This seems to have confused a lot of people. It's just a proof. Okay. So proof. So you want to show, right, I'll hit it again, epsilon greater than 0, the existent n dependent on epsilon, such that if n exceeds n, 1 over n squared plus 1 minus 1 is less than epsilon. Well, fix epsilon and take n to be any natural number. N to be any natural number such that n is bigger than 1 over root epsilon. Then, if n is past that chosen guy, we see that 1 over n squared plus 1 minus 1 equals 1 over n squared, an absolute value which equals 1 over n squared because n is in the natural numbers, right? right? Which, since n is bigger than 1 over root epsilon, we see that 1 over n is less than root epsilon. Which, again, since a less than b is equivalent to a squared. Let me write this up here. Sorry. Since n is bigger than 1 over root epsilon, we see that 1 over n is less than root epsilon, which is equivalent to 1 over n squared less than epsilon, since 1 over n and root epsilon are positive. Right? A less than b is equivalent to a squared greater than b squared for a and b positive. So, 1 over n squared plus 1 minus 1, which equals 1 over n squared, is less than epsilon, and we are done. Yeah, Rita.
I missed the connection. 1 over root epsilon is less than n. Why can you assume that big N is greater than 1 over root epsilon?
You choose it to be.
Oh, you choose.
You choose it to be. So if you take any n bigger than this, then n bigger than n gives it to you. Any questions about this? Right? So there's a scratch word part. You say, well, let's look at the tolerance condition. Consider the tolerance condition. Right? The tolerance condition is this, which is this. And then you try to figure out if there's some capital N, so that if n exceeds capital N, the tolerance condition is satisfied. Well, you take the tolerance condition and you transform it, and you say, oh, look, the tolerance condition turns into this. Right? Turns into n must be bigger than this. So just take your capital N to be something bigger than this. Right? The tolerance condition, we've transformed it into a n bigger than n kind of statement. Right? So just use that as your n. Right? And then, if n is bigger than this, then the tolerance condition is satisfied, because these are equivalent to each other. And
Wouldn't that, 1 over the square root of epsilon is less than n, mean that 1 over the square root of epsilon is equal to big N? Or why isn't it not that?
Remember the game, okay? Remember the game. The game is to find a capital N so that if little n is past there, then the tolerance condition is satisfied. Okay. Now we take the tolerance condition and say, the tolerance condition actually turns out to be equivalent to saying that n has to be bigger than 1 over root epsilon. Okay. So what should we take as our big N? We'll take big N to be anything bigger than 1 over root epsilon. Because then, if n is bigger than big N, that'll be bigger than 1 over root epsilon. N will get bigger than 1 over root epsilon, and your tolerance condition will be satisfied. Okay, so that's the line of thinking. Yeah, you can say.
Can we take big N as equal to 1 over square root of epsilon?
I mean, people do, but you know, again, because we've always been saying that big N is in the natural numbers, right? Just to be proper, you should probably say let N be any natural number that's bigger than 1 over root epsilon.
But why I can see it's equal to
Because you don't know this is a natural number,
Oh,
right? 1 over root epsilon is not necessarily a natural number.
okay.
So I don't want to say let N be this, let big N be this, because we've been saying all along big N is a natural number. But people do that. People are not don't care that much about that. So you could, I mean, if you say big N, let big N be this, I'm not going to care that much. Okay. But if you want to be if you want to be real stickler about it, then you should say big N is a natural. Take the natural number. Okay. Any other questions? John? No. Oh. No. Leah? Pen? No. Okay. So another example. I think there's no need to rush through this because this is sort of a weird way of talking. So this is an example. I think this is from your book, but we're going to do it anyway. So an is 2n plus 1 over 3n plus 2. Of the sequence, right? And you know what's going to happen, right? An is going to go to 2 things. But let's prove it. We have to prove it. So prove that an actually goes to 2/3, right? So again, you do your scratch work. You look at the tolerance condition, and you say, well, I want, so given epsilon, right, blah, 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 you have the tolerance condition, a sub n minus 2/3 has to be, less than epsilon, right? We want n such that n exceeding n implies this, right? So the scratch work is you take your condition and then you start simplifying it. Okay, so you say, okay, well, this is the same thing as saying. If you work it out, it turns out to 1 over 3n plus 2 is less than epsilon. So use your knowledge of elementary school, right? Your elementary school mathematics, you do this, right? Which is the same thing. And I can get rid of the absolute values because these guys are positive, right? I divide both, no, I don't. Okay, actually there's 2 things you can do at this point. So, 2 different paths at this point. So 1, you could say, well, let's continue along this line. 1 over 9n plus 6 is less than epsilon, is equivalent to, so continuing, 1 over 9n plus 6 is less than epsilon is the same thing as saying that 9n plus 6 is greater than 1 over epsilon. It's the same thing as saying that 1 over 9 epsilon is minus 2/3 is less than n. Okay, subtract 6 from both sides and then divide by 9. Again, masterful use of elementary school arithmetic. Okay, so that's it, right? That's it. We've transformed our epsilon condition into a n bigger than something condition, right? These are actually the same condition, right? So just take your n to be any natural number bigger than 1 over 9 epsilon minus 2/3 over 2/3. Right? Right? And if you want to write it out, you just write everything in reverse. Right? Proof given epsilon take n such that n exceeds 1 over 9 epsilon minus 2/3. Then if n is bigger than n, we see n is bigger than 1 over 9 epsilon minus 2/3, which is equivalent to 1 over epsilon being less than 9n plus 6, which is equivalent to blah, 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 is equivalent to 2n plus 1 over 3n plus 2 minus 2/3 in absolute value being less than epsilon. The end. Okay, so we just write everything in reverse here. Right? You say this is equivalent to this is equivalent to this, which is equivalent to this, which is equivalent to this, which is equivalent to the epsilon condition. Well,
I know maybe it's mathematically not a perfect proof, but what if you divide by n?
What if
Up
you
and
do-
down? The 2n plus 1 and 3n plus 2.
you divide by n.
12, yes.
So you say, let this be 2 plus 1 over n, 3 plus 1 over n minus 2/3. Right? Right? And, but then you still have to prove that, that there is an n past which, you still have to do it. Yeah.
Can I
So-
just-
So later on, it's true, you'll have some theorem that says, if you have the quotient of two functions and the limit of each of those functions goes to something, then you can just do it. Okay. So, but right now we're not going to invoke those theorems, so that you can get the feel of how to do these epsilon delta arguments. Yeah, John.
So should our formal proof at this stage always involve epsilon?
Yes. Yes. Everything at this point, you don't want to roll out the machinery yet. Okay. So later on, we're going to build these machines. Later on, you can use the machines and avoid this stuff. Right now, you have to get mastery of this sort of argument, because in the next course you're going to need it. Okay. Okay. Let me give the second path. Okay, so path 2. Okay, so we have, right, so we got our epsilon condition and made it equivalent to 1 over 3n plus 2 is less than epsilon. Okay. So here's another way of going. You could say, well, in fact, 1 over 3n plus 2 is less than 1 over 9n. Right? Because 3n plus 2 is bigger than 9. Right? 3 times 3n plus 2 is 9n plus 6. That's bigger than 9n. Right? So 1 over this is smaller than 1 over 9n. Okay. Right? Okay. So as long as 1 over 9n is less than epsilon, right? As long as 1 over 9n is less than epsilon, certainly 1 over 3n plus 2 is going to be less than epsilon. Right? Right? So look at this first one. This is saying that n is bigger than 1 over 9 epsilon. Right? Right. 1 over 9n bigger than epsilon is the same thing. Divide both sides by epsilon, multiply both sides by n. You get n is bigger than n is bigger than 1 over 9 epsilon. Okay. So this is a n bigger than n condition, right? It's not the best one, but this one implies the thing that we need. It's not equivalent to. In this one, we got one that was equivalent to. This one, we get one that's stronger than. Okay, it's not as good. It's actually, you know, like a rougher condition. But but we don't care, right? All we need is some n that works, right? So what we see is that taking n to be 1 over and taking capital N to be bigger than 1 over 9 epsilon, if n is bigger than 1 over 9 epsilon, then 1 over 3n plus 2 is less than epsilon, which is equivalent to the epsilon condition. Okay, so this is an easier way in some sense, right? So you slip to an easier condition to deal with, and easier, rougher, but stronger condition. It's more imprecise, but easier to deal with, and then you just use that n. Okay. Okay, we'll do more of this next time. Okay. So yeah, again, if you wanted to write it up, you just say, well, given epsilon, take n to be bigger than 1 over 9 epsilon, then, if n exceeds n, which is bigger than 1 over 9 epsilon, then we see that, 1 over 9n is smaller than epsilon. 1 over 9n is smaller than epsilon, which is equivalent to, which implies 1 over 3n plus 2 is smaller than epsilon, which blah 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 is equivalent to the epsilon coefficient. And that would be that would be the formal proof. Okay. Okay, and you see that this one's cleaner. Okay, that's it for today.